We're going to move on to our second presenter today, Dr. Dori Miller. Dr. Miller received her bachelor's degree in biology from Illinois State University and then completed her master's and PhD in neuroscience at the University of Wyoming. Her background is in basic and preclinical research, and she's published papers connecting a high salt diet to delayed puberty and metabolism. In 2019, she started her postdoctoral fellowship here at CU Anschutz, where she works with Dr. Wendy Court on the SCORE Project 1, and she's going to tell us about the work that she's doing on that.
Okay. Thank you, Carrie, for that introduction. All right, yes, so as Carrie said, I will be talking to you guys about the research that we have going on here. The research in progress is the bioenergetic effects of aging and menopause. This is the work of the SCORE project. It's SCORE Clinical Project 1. So the SCORE grant is a Specialized Centers of Research Excellence on Sex Differences grant. And our Colorado SCORE, the overarching goal of it is to advance the knowledge of the impact of gonadal aging on the regulation of bioenergetics, abdominal adiposity, metabolism, and disease risk by conducting mechanistically driven research across basic to clinical translational spectrum. So I'll be talking today about Clinical Project 1, which is led by Dr. Wendy Court. And then we have, there's also a preclinical project led by Dr. McLean and a basic project led by Dr. Clem. So the clinical project is subtitled BEAM for the bioenergetic effects of aging and menopause. So today I'll be going through the background of why we developed this project, the aims of the project, methods and preliminary data, and then our current status. So the background is that body composition shifts during the menopause transition. And so even without excess weight gain, there is still a fat deposition chain shifting from the women shift from storing fat in more of the pear shape thought. So that would be fat storage in the subcutaneous depots of the hips and thighs, to moving to fat storage to the visceral abdominal compartment. So this is supported by numerous cross-sectional and longitudinal studies that say that postmenopausal women have increased abdominal adiposity compared to their premenopausal counterparts. And then we also have some evidence that suggests that estrogens are protective against this. So we find that in studies that looked at hormonal replacement therapy. There have been studies that have shown that that attenuates weight gain, waist circumference, fat mass, and specifically trunk fat mass. And so here in this chart, in this graph, you can see that this is a hormonal replacement therapy, and that there is a significant reduction in waist circumference with hormonal replacement therapy. We also can see that women who undergo oophorectomy before the age of 40 have increased relative body fat content and waist girth when compared to women with intact ovaries. We also have evidence that GnRH agonism increases fat mass in premenopausal women. So GnRH agonism operates against targeting the fact that GnRH must secrete in a pulsatile manner to secrete pulsatile, to stimulate the secretion of pulsatile LH. So with an agonist where it's a continual bolus of GnRH, you have an initial surge phase of LH response and then a suppression period. So after GnRH agonism, which will suppress the entire HPG axis, there are numerous studies that show that there is an increase in fat mass in premenopausal women given a GnRH agonist and a decrease in fat-free mass. And then we can see that borne out specifically in the trunk region, that there is a change in fat mass that is majority of it is within the trunk. There's also evidence that there could be a role for glucocorticoid metabolism in abdominal adiposity. So the idea comes from the fact that in Cushing's disease, which leads to excess cortisol production, there's that significant abdominal adiposity, which is a hallmark of Cushing's disease. And so we've planned our experiments to address glucocorticoid metabolism, and specifically we're addressing the enzyme 11-beta-HSD1. We know the HPA axis secretes CRH from the hypothalamus, stimulating ACTH from the pituitary, which stimulates cortisol and cortisone release from the adrenal glands. And then within adipose tissue itself, we have 11-beta-HSD1, which can convert cortisone to cortisol. This enzyme is also present in the liver. And then systemically, we have conversion of cortisol to cortisone by 11-beta-HSD2 in the kidneys to prevent the activation of the mineralocorticoid receptor within the kidneys. So by taking a look at systemic cortisol, we're actually getting a measure of the cortisol that's produced by the adrenal gland and 11-beta-HSD1 within the liver and adipose tissue, subtracted by the cortisol converted by 11-beta-HSD2 in the kidneys. And then if we were to look at adipose tissue specific cortisone conversion, that would then be a measure of 11-beta-HSD1 within adipose tissue specifically. And so here is some background about how cortisol response, why we also think cortisol response could be a factor playing a role here. So when there was a meta-analysis of 45 different studies, they found that there was an exaggerated cortisol response to either pharmacological or a psychological challenge. And that effect was about 3 times greater in women than it was in men. And then there are some papers that suggest that estradiol may reduce cortisol response to stress, but this has not always been seen. So this is one of the reasons why we want to investigate this further. The HPA, so this is some of our preliminary data. The HPA response is blunted after GnRH agonist therapy. So this is a group of premenopausal women who were given GnRH agonist, which is going to lower both estrogen and FSH. I'll get into it in a little bit why we also think FSH may be playing a role. And then we also have a GnRH antagonist with estradiol add back, which will raise FSH in a low raise E2 in a low FSH environment. We take a look at the area under the curve in response to challenges. In response to a corticotropin releasing hormone challenge. So we took a look at the ACTH, cortisol, and cortisone responses. And you can see here that we're seeing a significant decrease in the area under the curve in the group that was given the estrogen add back. So our aim one is to determine whether adipose tissue and systemic glucocorticoid metabolism are regulated by estradiol. So we have 2 hypotheses here, and that relates to how we're able to measure the actual activity of 11-beta-HSD1. So our first hypothesis is that the conversion of cortisone to cortisol by 11-beta-HSD1 in abdominal subcutaneous adipose tissue. So we'll be taking a look at the activity of the enzyme specifically in abdominal adipose tissue will be lower in the estradiol add back group than in the placebo in both pre and postmenopausal women. And then our second hypothesis is that the systemic cortisone challenge, so that will be the sum of all of the cortisol conversion by 11-beta-HSD1 and then the conversion of cortisol back to cortisone, that will be subtracted by the activity in the kidney by 11-beta-HSD2, will be lower in the estrogen than placebo in both pre and postmenopausal women. And so we have 4 or 5 different groups. We have our premenopausal women who will be given a GnRH antagonist. So we switched to using a GnRH antagonist because you don't have to have that initial bolus period where there's an initial LH surge. And instead, you just get GnRH antagonism, which will suppress the entire HPG axis. And that will be with placebo or estradiol add back. And then we'll have a group, 3 groups of postmenopausal women who receive either the GnRH antagonist with placebo, the GnRH antagonist with estradiol, or a placebo group. And so this is going to allow us to isolate out the effects of FSH and E2, which I will explain as part of our secondary aim. So recently it's come to light that there may be some metabolic actions of FSH, and this primarily comes from a Nature paper published in 2017, which found that using an FSH antibody to block the actions of FSH resulted in a significant reduction in abdominal adiposity. So you can see in their micro CTs, there's a significant reduction in that visceral adiposity with the antibody group, and that was present in OVX or sham animals, indicating that it was not determined by the estrogen environment. And then over here, you can also see that, so we have here the IgG group is our control, and then we have the antibody group. We have a significant reduction in adipocyte size. So the antibody gave a 30% reduction in total fat, a 30% reduction in subcutaneous abdominal, and then it really targeted that visceral fat by a 70% reduction. There were also bone effects, which we are also examining in the SCORE Project 1 beam. So with the antibody, they showed a significant increase in bone mineral density. And so this is, this is not the antibody. This is actually FSH beta knockout. So in the heterozygous FSH beta knockout, we see that there is a significant increase in bone mineral density. So then the FSH increases before estradiol declines during the menopausal transition. And this is particularly interesting because we start to see some effects of the menopausal transition, like decreased bone density, increased abdominal adiposity, decreased flow-mediated dilation that Matt just talked about. We see those things start before estradiol actually starts to decline, during the time when FSH is rising. So our M2 is a proof of concept, so it doesn't have attached hypotheses. Instead, this is meant to be hypothesis generating. So M2 is to investigate the effects of suppressing FSH for 24 weeks in postmenopausal women on resting energy expenditure, bone mineral density, visceral fat area, and flow-mediated dilation. So to test this, we're going to simply continue those 3 groups of postmenopausal women on their respective treatments for another 12 weeks. And then measure at 24 weeks all of those different outcomes. And our aim 3 is collaborations with SCORE projects 2 and 3. So we'll be collecting adipose tissue at baseline 12 weeks and 24 weeks from all of these different groups of women. And so this will give these other projects the ability to evaluate independent effects of FSH and E2 on mitochondrial density, UCP1 expression, which is an indicator of Beijing in adipose tissue, and regulation of bone marrow-derived adipocytes. All right, so the methods and preliminary data that we have for aim 1. So as I mentioned, we're going to be taking a look at the microenvironment the activity of 11-beta-HSD1 within adipose tissue specifically. So we're going to do that by using a microdialysis probe where we pump in micro amounts of cortisone into the fat tissue, and then we collect the converted cortisol. And then we're using subcutaneous abdominal adipose tissue because it'll be a minimally invasive procedure. We'd obviously like to take a look at visceral fat if at all possible, but subcutaneous abdominal adipose tissue is metabolically closer to visceral fat than either gluteal or femoral fat is. And then some previous research has suggested that there's no depot-related differences in either 11-beta-HSD1 mRNA level or the measured conversion of cortisone to cortisol. And our preliminary data suggests that if we take the experimental probe, so that's we're pumping micro amounts of cortisone in and measuring the output of cortisol. And then we also have a control probe that we can subtract from the experimental probe, which will be pumping in, again, micro amounts of saline and collecting the outputted cortisol. So that'll normalize for the amount of cortisol that's actually in the system. So together we call that the MCC index. And the index is highest in postmenopausal women. It is secondarily higher in premenopausal women that have been treated with a GnRH antagonist. So they'll have low FSH and low E2. And then it is the lowest in premenopausal women in the early follicular phase with the highest estradiol. And then to determine if there's any local blood flow alterations by the cortisone that we put into the system, we're using an ethanol dilution technique, which will monitor the qualitative changes in blood flow so that we can make sure that the blood flow isn't changing differently. And then we'll be doing part of AIM-1, the secondary hypothesis. We'll be doing an oral cortisone challenge, which will take a look at the area under the curve after a cortisone acetate pill. So we'll give participants cortisone acetate and then take blood draws at time 0, 30, 60, 90, and 120, and then we get an area under the curve from that. And so here in this, you can see that this was 4 premenopausal women in the early follicular phase, then treated with a GnRH antagonist, and then treated with estradiol. And you can see that the area under the curve was higher after the antagonist, and then it was rescued by the addition of the estradiol. And now I'll move on to the methods and preliminary data for AIM-2. So we'll be doing, using DEXA to measure bone mineral density. So here is this is a hypothetical changes in bone mineral density. If the decrease in the placebo group is related to both decreased E2 and FSH, like we hypothesize. So we'll have, these are all postmenopausal women. So placebo, they'll have low estradiol and high FSH. Treated with the antagonist and placebo, they will have low E2 and low FSH. And then the GnRH antagonist and E2 group will have high estradiol and low FSH. And that should result in the lowest group with the lowest bone mineral density should be seen in the placebo group. We expect to find a slight rescuing effect of the GnRH antagonist, and then the GnRH and antagonist plus estradiol should have the highest bone mineral density, is what we hypothesize. We're also measuring resting energy expenditure. So in that Nature paper that I mentioned previously that had done the follicle stimulating hormone antibody, they had shown that there were decreases in energy expenditure in the groups that had been given the antibody compared to the IgG group, which is the control. So they found that in both male mice on the high-fat diet, and they found some differences in female mice. And they found that, again, in either the sham or the overactimized mice, indicating that FSH was playing a role regardless of estradiol environment. And then we'll also be measuring visceral fat area via CT. And again, that comes from that Nature paper where they found a significant reduction in the antibody-treated group's visceral fat area via micro-CT. And we're working with Matt and Carrie Moreau to measure flow-mediated dilation. And so again, this comes from the idea that there is a decrease in flow-mediated dilation that occurs before the estradiol decrease in postmenopausal women during the same time that FSH is increasing. And so some of the preliminary data that Carrie has gathered suggests that with aging here, so these are baseline, you can see a decrease over time with flow-mediated dilation, very similar to what Matt showed with men. And then we have a rescuing effect when you have the GnRH antagonist with estradiol. However, some of our preliminary data suggest that so postmenopausal women with GnRH antagonism, E2 and FSH, there wasn't a rescuing effect like we would have hypothesized. However, these women were just 4 days in the GnRH antagonism and then the GnRH antagonism plus estradiol groups. So perhaps FSH will need longer to actually see an effect. And we'll hopefully see that in our women that are under suppression and estradiol add back, with or without estradiol add back for 24 weeks. So our current status, we received our approvals in 2019. We have had really successful recruitment so far, but and right now we have had 9 women randomized, but we did have to withdraw 4 women during the initial closures because of the COVID-19. And right now we have 5 women that are currently under intervention. And so we're hoping to keep moving forward with this research. And we've had pretty good success recruiting from a representative population from Denver. And as you can see here, this is our postmenopausal accrual. So we have 5 women under intervention. Right now, we're under an institutional suspension of recruitment, and we're hoping to get back started here soon. We're holding off on enrolling the premenopausal arm right now, but we're hoping to get back started in June of next year. So with that, I'd like to thank the BEAM study team, Dr. Wendy Court, Kathleen Gavin. I'd like to also thank the entire image group and the Department of Geriatrics, or Division of Geriatrics. I am on the Division of Geriatrics T32, and I want to thank them for their support, as well as the various NIH grants that fund this research. Thanks.